Hello, I'm Eric Vallon, and I will be talking about the force-velocity relationship and more specifically the Hill's mechanical model. So I'll start with my interests. I'm really interested in muscle anatomy, physiology, the force-velocity relationship, and all things physiology in that nature because I really just love muscles and I love the skeletal system. And without the skeletal system, we wouldn't be able to truly understand or comprehend kinetics, human kinetics that is, and human kinematics. And movement is regulated and carried out by the skeletal system. So without muscle action and our understanding of muscle action to produce force, we wouldn't be able to understand later concepts that are in the course. So to look at the force-velocity relationship and specifically force and tension, we need to look at the microscopic level of the muscle just so we can understand how force and tension are produced there, so we can look at the whole muscle group as a whole. So I'm gonna try to keep this short for sake of time. Basically, the sliding filament goes as this. As a muscle receives a stimulus at the neuromuscular junction, it's going to pump calcium into the sarcomere once it gets stimulated. And the sarcomere, as just a refresher, is the fundamental unit of the muscle. So whatever happens to the sarcomere is going to be happening to the muscle as a whole, basically shortening and contraction. So upon binding of calcium to troponin on the actin thin filament, the active site is exposed. ATP is hydrolyzed on the myosin head, and myosin is going to make a cross-bridge formation with that actin. The myosin heads then do a power stroke, and they're going to pull the actin filaments inwards, and the actin filaments are in a hexagonal array around these myosin thick filaments, so it pulls a bunch in at the same time. And this basically shortens the sarcomere, and it's continually attached and hydrolyzed, and this ensures cross-bridge cycling, and where the myosin attaches to the thin filament is where you get the tension development. So the next topic we're going to talk about is the force-velocity relationship, and this needs to be touched on to segue into the main topic of discussion, which will be the biomechanical topic known as the Hill's mechanical model, or theory known as the Hill's mechanical model. And I want to talk about this first because I'll just explain the graph. So you see that to the right and to the left of the graph are concentric and eccentric contraction. And the y-axis is force, so you increase the force on the y-axis, and the x-axis, in either direction, you're increasing your velocity, so Vmax is your maximum velocity. So you can see as you shorten your muscle and you increase the velocity of shortening, your force production and force generation is going to decrease, but it's the opposite for eccentric muscle contraction. As you increase the velocity of your muscle lengthening, your force generation is going to increase. And this is why I'm talking about this, because this has been an unanswered question that I've actually had in all of my other courses. So it was really awesome to see this force velocity relationship and then have the answer, which is the Hill's mechanical model. So the counterintuitive answer to the eccentric motion generating more force with increased velocity is kind of explained by this length tension curve. So as you look at the L naught, or length of zero, which is the dotted line that goes up to the apex, as you move from the apex to the left of the graph under that total tension, the filled in line, you can see that would be considered concentric contraction, and you can see that the tension decreases. But if you go back to that apex right at the dotted line and you move to the right, this would be eccentric contraction. And that dotted line actually isn't the case with eccentric contraction. The filled in line that kind of slopes down and then increases its slope upwards is the eccentric contraction. And this line is due to the passive stretch dotted line that you can see starts from L naught basically. And the passive stretch is contains two things of the Hill's mechanical model: the parallel elastic components and the series elastic components, and I will touch on these in just a second. So finally we get to the bread and butter of my talk, which is the Hill's mechanical model, and it's the bread and butter because it's answered all of my unanswered questions. So basically, though, that length tension curve that I just showed you, the reason why it spikes up again with eccentric motion is because of the series elastic components and the parallel elastic components. And the series elastic components are just these structural microscopic proteins like titin and nebulin, and these allow stretch and recoil, and you'll see it in the next depiction that I show you of the slide. And then the parallel elastic components are the same thing, except for on a bigger scale. They're the fascia and the endomysium and the epimysium and paramysium and all the connective tissue that surrounds whole muscle and muscle fibers. And these also just allow stretch and recoil of these structures, and this stores mechanical energy within them to increase tension. So this basically is a depiction of the Hill's mechanical model, and as you can see those coils there, if you imagine that figure to be elongated, those coils would be stretching out, contributing to stored energy and helping increase tension and increase force. And then another thing within this model is the contractile components, which I forgot to mention, and those are just the contractile proteins within the sarcomere, myosin and actin. So the biggest difference between the textbook definition and my definition is my definition includes why eccentric contraction generates greater force development with an increase in velocity. And it's basically the stored mechanical energy not only in the surrounding muscle tissues, but also the integral proteins of the sarcomere. When I think of the application of this Hill's mechanical model, I think of training. So, with eccentric contraction, not only are you going to increase your time under tension, which is going to generate a greater protein degradation, you're going to increase your delayed onset muscle soreness and you're going to increase your satellite cell response and you're going to get better gains because of that. And that is the end. Thank you.